Hello fellow engineers, welcome to my first YouTube video. I am Dr. Yogesh and I work mostly with antennas, RF, microwave circuits. And in fact, most part of my career I have been developing instrumentation for radio astronomy and satellite communication applications. With this video, I am going to start a limited episode web series giving details about and various aspects of instrumentation related with front-end system engineering for radio astronomy. And there is a reason to start this particular web series today itself, because today is 15th of September. In India, we celebrate 15th of September as Engineers Day, in memory of Sir Vishvesvarayya's work during pre-independent era of India. He was also awarded for his engineering contributions the highest honor in India, referred as Bharat Ratna, in 1955. So remembering him, I am going to formally start a web series with which we will discuss front-end system engineering for radio astronomy. So there are a lot of questions now. For some users, the radio astronomy subject itself is new. So I have to very briefly first introduce the subject of radio astronomy. Then I will talk about how a radio telescope looks like, and finally I will narrow down to the subject of the web series, what exactly is front-end system engineering. And therefore, before moving forward with these videos, I want to say a word or two about targeted audience for this web series. This particular web series is mainly for students of electrical engineering around the globe, also students who are reading master level courses in electrical engineering, doing their MTech degrees, etc. and reading courses like antenna engineering, RF engineering, microwave engineering, electromagnetics, and so on. Because all these sub-branches of electrical engineering are definitely required to develop a sensitive front-end system for radio astronomy applications. So let me first introduce to you the subject of radio astronomy. However, we are not going to discuss in-depth radio astronomy. Rather, what we are going to discuss in this web series is technology associated with radio astronomy. So what is radio astronomy? In very simple manner, radio astronomy is to study celestial bodies by receiving radio signals from them. And it is astonishing fact that like we receive light from many celestial bodies like sun, moon, planets, and so on, many celestial bodies, they do emit radio waves, X-rays, gamma rays, UVs, etc. And then with radio astronomy, by using very sensitive radios, we try to catch the signals from these celestial bodies and try to study and analyze them. Having told you the definition of radio astronomy, one must ask, how does it all started? And you could see on the screen, actually it started by an engineer named Karl Jansky in 1932. With his radio, he was able to conclusively prove that he was receiving some disturbances and they were not man-made, and they were coming from outer space. Nowadays, it is very clear that those disturbances are nothing but the radiation originated from our own galaxy Milky Way, and it is not at all an extraterrestrial intelligence. Post Karl Jansky, it was Groth Reber, who was an amateur astronomer, but he put lots of efforts to study radio astronomy. And actually, with his own work, one could say that the subject of radio astronomy was born around 1950s. And he was also the first one who has used parabolic dishes to receive the signals from outer space and do a detailed radio map of our universe. However, the technology at that time was definitely not as mature as we have today. And in today's world, we have highly sensitive, very modernized radio telescopes. So like Newton and Galileo, they use their optical telescopes with mirrors and lenses. In today's world, radio astronomers, they use big radio telescopes, and they are going after constructing even bigger radio telescopes such as square kilometer array. So having said that, what exactly is a radio telescope? typically, as you could see in the slides, the radio telescope like Giant Microwave Radio Telescope, some 200 kilometers from Mumbai in India, Very Large Array in New Mexico, ALMA in Atacama Desert in Chile, or Jodrell Bank in Manchester. They all have something in common. What they have is a very big dish with which you collect the radio waves coming from outer space, and then they get focused at the focus of the parabola, where they get converted into the electrical signals, and thereafter we further amplify it. So with this, we are actually narrowing down our discussion to the front-end system engineering. So this particular thing is analogous to our human eye. Like our lens in our eye, it collects light, and that light gets focused on the retina, which actually converts the light into the signal which brain can interpret. Similar to that, a dish with a feed horn and an amplifier receives the signals from outer space and convert it into an electrical signal. Many modern telescopes are no longer just a single dish radio telescope, but rather they are an interferometric array of many such dishes. However, we are not going to discuss about interferometry and other techniques in radio astronomy. This particular web series is solely meant for front-end system engineering for radio telescope. So now let me explain and define what is front-end system engineering. As you could see on the next slide, I have made a simple block diagram of the system, that we have a dish. The signals which come from outer space, they hit the surface of the dish or the reflector, and then they get focused at one particular point. At that particular point, we have some sort of antenna. In most of the cases, it is feed horn. What is a feed horn? We will definitely cover in our web series. This feed horn converts these electromagnetic waves into electrical signals. They are very weak, so naturally we have to amplify it. And then what we use is a low noise amplifier. That is an amplifier which adds very low noise and amplify the signal, so your signal to noise ratio is really high. Post amplification, you could have some sort of filtering and a detector to convert the signal into baseband. One could, in a very simplified manner, say that a feed horn with a low noise amplifier, maybe a detector with some filtering, is a front-end system. And all engineering associated with this particular blocks of the systems we are going to discuss in this web series. However, in modern radio telescopes, mostly what you have in front-end system is horn and amplification, low noise amplification, and some filtering. And then you try to take this data, digitize it, take it to the main control room, main server room, further process it, build image out of it. And all this can be taken into another system which is called as back-end system for radio astronomy. Again, we will stick to our original topic, that is to discuss front-end system engineering. So, having defined what exactly front-end system is, now I will try to talk about more detailed block diagrams of the front-end system developed at Tantrayut Telecommunications in L-band for radio astronomy. As I have said, what we are going to discuss is front-end system engineering in L-band. L-band, which is a frequency range of 1 to 2 gigahertz, and to be specific, what we are going to discuss is system development in the frequency range of 1050 megahertz to 1620 megahertz. This is a very attractive band for radio astronomy applications. And in next slide, what we will try to discuss is the actual block diagram of a working L-band system for prime focus reflectors used for radio astronomy applications. So to start with, as I have said before, that we need a feed horn. What is a feed horn? That we will cover later on in the series, but typically in this particular case, to explain the block diagram, we are going to use a choke horn, which is one kind of feed horn. So choke horn receives the signals which are incident upon your prime focus reflector dish, and this particular choke horn sits at the focus of the dish. So at the end of choke horn, the signals are still guided waves, they are not converted into electrical signals. So natural way to proceed is to put some sort of mode converter so that you could convert guided waves in circular waveguide into an electrical signal in coaxial waveguide or coaxial cable, and then put a low noise amplifier. But we have a big challenge here, because we want to receive very weak signals coming from radio sources from outer space in presence of very strong mobile bands which we use for our day-to-day communication. This is like you are driving at night and a car is approaching towards you, and the driver forgets to put the car's light to the dipper. So basically all your eyes are completely flooded with light and you can't see anything on the road. Similar thing happens in radio astronomy instrumentation or engineering associated with it, that we have very strong radio waves originated from our mobile towers, and they completely saturate the receiver, which is highly sensitive and cannot handle large amount of power. So we have to first get rid of the mobile bands which are anyway present. We all use mobile, we cannot get rid of mobile. But at the same time, try to achieve equal sensitivity so that we could receive these very weak signals from outer space. So what we are going to put just after the choke horn is a waveguide filter, and especially we will be using circular waveguide filter, because this particular filter can support both orthogonal polarizations at the same time, and since we are using waveguide technology, the loss in this particular filter would be very low, which is definitely desired in radio astronomy applications, because you don't want any lossy component for these already weak signals before you amplify it. Post circular waveguide, what we have is a polarizer. So polarizer are of different types, and what they basically do, that they separate polarizations into two orthogonal linear polarizations or two orthogonal circular polarizations. In our system development, we will be using a septum polarizer which separates incoming waves into right hand circular polarization and left hand circular polarization. Now the signals are converted from waves to electrical signals, and we could amplify it with what is device called as low noise amplifiers using high electron mobility transistors. So at the end of the low noise amplifier, as such, one could say that the front end system is over. But we need many more features when it comes to front end system for radio astronomy. The next obvious feature which many radio astronomers want, that they want to inject a calibrated noise, a calibrated white noise into the system prior to the low noise amplifier. With this, they could try to calibrate their entire receiver and try to get better sensitivities in their observations. To do that in engineering way, first we need some sort of noise source which is white. White means it gives equal power at all frequencies, say between 1 to 2 gigahertz. Then we have to inject that noise before low noise amplifier, and usually it is done by a directional coupler. Again, achieving very low loss directional coupler is highly desirable. Moving forward, post low noise amplifier, as such, if you have highly competitive digital backend, you could straight away digitize entire RF bandwidth at once. But it really depends upon system to system and what sort of D to A conversion boards you have. So in this particular application, what we are going to offer is to have entire 600 megahertz bandwidth in one go or to divide this particular bandwidth in each sub 100 megahertz channel, like 1050 to 1150, 1150 to 1250 megahertz and so on. To do that, one has to design a filter bank. So each filter is for one particular center frequency, and those center frequencies are separated by 100 megahertz. And one particular filter which could offer you the entire band. But these are just filters, and you have to switch these filters properly so that you could get a digitally switchable filter bank. So this is also an additional feature which many radio telescopes have, that they could use some sort of filter bank to select particular band for observation. And finally, this is more for engineering use, that one could put an absorptive type of RF switch, so one could terminate the output of the system off for other technical maintenance reasons. Having said that, there are many different challenges in each and every block development, and this is what we are going to cover in this web series. This entire block diagram, what you have just seen now, we are going to take one block at a time, and we will try to show the challenge in that particular design, how that design is done, how it got fabricated, and then proof with measurements. So I have talked enough. Do you now really want to see the real system, how all these block diagrams look like in reality? Wait a moment. I bring this system and we will continue our discussion further. Hello again. In previous part of the video, we have discussed the block diagram of Tantrayut's L-band field system. And now I am going to show you the real fabricated and working prototype of this system. So what is in front of you is fully assembled and working prototype of this particular system for radio astronomy. So to start with, what we have at the bottom is the choke horn, which is designed to suit with its radiation pattern is suitable for f/d of 0.4 of the prime focus reflector, but one could also redesign this horn for other focal length to diameter f/d ratios. Then this is the main thing, which is a circular waveguide filter. It supports both polarizations simultaneously, and it gives 45 dB attenuation to both mobile bands, which is really good to do interference-free radio astronomy applications. And similarly, this system can also be tweaked or redesigned for SATCOM applications. After the circular waveguide filter, what you see coming at the top, protruding at the top, is a septum polarizer. And septum polarizer has both outputs. So on this side you have right hand circular polarization output SMA connector, and on the other side there is a left hand circular polarized connector. Followed by that, as we have discussed in our block diagram, there is a directional coupler to inject noise into our measurements, a reference noise. Followed by that, there is a low noise amplifier. On both sides of the systems, there is filter bank for left hand and right hand polarization, which is switchable digitally. And finally, an output switch to terminate your RF output on or off. At the back end of the system, what we have is a noise source along with a switch so that you could switch noise source on and off, and a power splitter so that we have equal power of noise in both polarizations. This particular black box, as of now, it has an Ethernet port, and this Ethernet port is basically an interface to the external world so that you could send commands over Ethernet and control all these RF electronics inside. And actually the system will come with this kind of interface plate. So you have RF output for left hand circular polarization, right hand circular polarization, Ethernet and DC connector. So if you are interested, keep watching my YouTube videos, and in the next video I will start with very first component of the system, that is choke horn. And if you have interest in developing such custom systems for your application, whether it is radio astronomy or SATCOM, you could always contact me on consult@tantrayut.in. Thanks for watching.